Hello and welcome back. We'll start section 2.5 in this video, which is all about graphing certain kinds of functions and how to transform these functions into one another. So we'll start out with some common functions. The first type of function that we'll see are just constant functions. So when we look at f of x is equal to c, we think f of x is going to be the height of the function, and it's always going to be equal to c. So our function is going to look something like this, where the point where it crosses, this will be c. The domain of this function, all of the available inputs into the function, well, we can put anything we want into the function. The domain, all of the possible x values are literally every number. The range is all of the possible outputs of the function, and that's only ever c. So the range of the function is only one number, so it is a set that only has c in it. When we look at this, this function is going to be constant, hence the name, on the entire interval from -infinity up to infinity. It never goes up or down, meaning it never increases or decreases. And then furthermore, this is an even function. If we flip this across the y-axis, we get the same function. Looking at the next one, so the identity function is the function where f of x is equal to x. Whatever you plug in, it preserves the identity, and it just comes out the other side. So the identity of x is preserved. This function, whatever you plug in, is the height. So at 0 we have 0, at 1 the height is 1, at 2 the height is 2, and this is just a straight line. It's a very easy function to remember. The domain is what values can we plug in? Well, we can plug in anything. So the domain is all the way from -infinity to infinity. The range, what are all the possible heights? Well, all the possible numbers that we can plug in. So the different heights of the function, the range, is going to be the entire y-axis. This is increasing forever. So this is increasing on the interval from -infinity to infinity. And this is an odd function, not an even function. Again, if we rotate this 180 degrees, we still have the same thing. So this is an odd function. The next function we'll look at is the absolute value function. And the absolute value of x is never negative, so I won't graph anything below the line. As we graph this, f of x is equal to the absolute value of x. When we plug in 1, we get 1. When we plug in 2, we get 2 and 3. So this side will simply go straight up. But when we plug in negative numbers, the absolute value of -1 is 1, -2 is 2, -3 is 3. So this side also goes up. So we have this V shape here. So the domain, what values can we plug into the absolute value? Well, we can plug in anything we want. But the range, all of the possible heights, we can only get positive numbers if we plug something into the absolute value. So we can get 0 by plugging in 0, and any other positive number, but we can never get a negative number. So the range is going to be anything 0 and up. We can see that on the left-hand side, this is a decreasing function. It's going down. So this is decreasing all the way up to 0. But on the other side, it's increasing. So it's an increasing function from 0 to infinity. And this is also an even function. If we flip it across the y-axis, we get the same thing. A few left to look at. So we've got the standard quadratic function. So this is f of x is equal to x squared. 1 squared is 1, 0 squared is 0, Negative 1 squared is 1, and this guy looks a lot like the absolute value, except that it's nice and smooth. We don't have that V shape, we have more of a U shape here. The domain, what values can we square? Well, we can square any number. So the domain is going to be from negative infinity to infinity. The range of the function, what values can we get? Well, again, we can't get any negative numbers, but from 0 on up, we can get every single number. Again, just like the absolute value function, it's decreasing on 1/2. So decreasing on the interval from negative infinity up to 0, but it's increasing on the interval from 0 up to infinity, and this is also an even function. If we flip it across the y-axis, we get the same function. We get the same graph. The square root function looks a lot like the quadratic function, x squared, but we flip it over onto its side. So the square root of 0 is 0, the square root of 1 is 1, and it kind of looks like, let me draw this a little better, and it kind of looks like a parabola, but only half of a parabola since the square root is always positive. So the domain here, what numbers can we take the square root of? Well, we can take the square root of any positive number, including 0. And the range, well, we can get any positive number for the range as well. So we can see that this is increasing on its entire domain, so from 0 to infinity. But this is neither odd nor even. This doesn't have reflectional symmetry across the y-axis, and it doesn't have rotational symmetry either. We've got the standard cubic function. So this function, so 0 cubed is 0, 1 cubed is 1, and as you cube numbers, they grow quite quickly. But negative 1 cubed is going to be negative 1, because negative 1 times itself 3 times, the negative sign won't cancel out. So we have this function that kind of looks like this wave coming up. The domain, what numbers can we cube? Well, we can cube any numbers that we want. So the domain is the entire x-axis. The range, well, we can get any height that we want as well. So any y value is possible. And as we move from left to right, the function is always increasing. So it's increasing on the entire real line. And this is an odd function. Again, this has rotational symmetry, 180-degree rotational symmetry. And when we look at x cubed, this has an odd power. So because it only has one odd power, it's an odd function. And then we've got the cube root function, which is going to look exactly like this guy, except turned over onto its side. So we've got something that looks like the following. So note that this increases slower and slower and slower, whereas this increases faster and faster and faster. But again, the domain is going to be every number. We can take the cube root of every number. The range is going to be every number as well. Every number has a cube root. This is always increasing. And this is also an odd function. Here we can't use the power of x. It doesn't quite work. But it's an odd function because it has rotational symmetry, 180-degree rotational symmetry. So these are the common types of functions that we'll be graphing in this section. But let's see what happens to the graphs when we modify them. If we graph f of x is equal to x squared, well, this is the parabola that we just saw. So 1 squared is 1, 2 squared is 4, so we'll be coming up kind of in this U shape, kind of like this. But now let's look at the graph of x squared plus 1. So what does adding 1 to this function do? Well, if I plug in 0, 0 squared plus 1 is 1. 1 squared is 1, plus 1 is 2. And you can kind of get a sense that what we've done is we've shifted the graph up. So if this was our original function, f of x, our new function is going to be shifted up a little bit. So what we'll notice is that g of x is in fact just f of x plus 1. So when you add 1 to a function, it shifts it up 1. Now we could play the same game by subtracting. So let's take x cubed minus 3. So when we plug these values in, if we plug a 0, 0 squared minus 3 is minus 3. 1 squared minus 3 is going to be minus 2. 2 squared minus 3, well, that's 1. So we start to see that our parabola has now shifted down. I apologize for my bad drawings, but essentially we can see that when you add a number to the function, we're going to shift it up, and then when we subtract a number, we're going to shift it down. So let's formalize this. So vertical shift. The graph of f of x plus c is shifted up. It's just the same thing as f of x, but we've gone up. Instead, if we look at the graph of f of x minus c, it's the same shape as f of x, but we've shifted it down. So let's do a quick example. Here we have g of x is the absolute value of x plus 3. So when I look at this, I go, oh hey, we have the graph of f of x, we have the graph of the absolute value of x, and all we've done to it is added 3 to it. So this is fairly straightforward to graph. The graph of the absolute value of x looks like this v, and since we've added 3 to it, we've shifted it up 3. So when you take a function and you add a number to it, that means that we are shifting it